Alright, hello everybody. This video is going over the fifth lesson of Unit 2, which is on Lewis diagrams. So today our understanding is that molecular compounds are arranged based on Lewis diagrams and valence shell electron pair repulsion theory, also known as VSEPR. Today's objective is to represent a molecule with a Lewis diagram. So when we are making Lewis structures, essentially you're going to see a bunch of letters. The letters are going to be atoms. You're going to see dots. The dots are going to represent electrons. And then you're going to see lines. The line represents 2 electrons. So each line or bond is representing 2 electrons. Now, how in the world do we figure out what bonds are being formed? Well, let's look at a diatomic molecule to start. So let's look at fluorine. If we have fluorine gas, there's a reason that it exists as 2 fluorine atoms bonded together. And that's because fluorine by itself has 7 valence electrons, which is extremely unstable because it's really close to becoming stable with an octet. So if you have a sample of fluorine atoms and they want to become stable, what they will do is form a bond between those 2 lone electrons so that each fluorine is going to share both electrons. So if we're looking at the left fluorine, this fluorine now has 2, 4, 6, and 8 because it's sharing that 1 electron from the other fluorine. And then if we look at the right fluorine, we have 2, 4, 6, and 8 because they're sharing. So each fluorine is now stable, which is why fluorine is a diatomic element, because it is more stable as a pair than it is by itself. All right, so before we start drawing Lewis structures, it's really important that you understand the number of valence electrons of all the elements on the periodic table and how they're going to want to bond. So for example, if we're looking at an element from group 1, our group 1 elements have 1 valence electron. So if you were to draw the dot structure of hydrogen, hydrogen just has 1 electron. So if it were to bond in a molecule, all it's going to do is form 1 bond. So the only thing hydrogen can do is form 1 bond. It's not going to form more than that because it's in the first energy level, so it's maxed out at 2 total electrons. So if you ever have hydrogen in a Lewis structure, just know it can only have 1 bond. That is the only choice that we have. Then we go to our group 2 elements. Those have 2 valence electrons. So something like beryllium has 2 valence electrons. And we do see beryllium taking part in covalent bonding. And since it only has 2 valence electrons, it can only form 2 bonds. So beryllium is usually going to be forming 2 bonds with no lone pairs on the central atom. Then we go over to group 13 elements, which have 3 valence electrons. We also see boron covalently bonding, and boron, group 13 element, has 3 valence electrons. So if it were to bond out, those 3 lone electrons are pretty unstable. They want to become stable by forming a bond and completing that stability. So if boron were to bond covalently, it would form 3 bonds and have no lone pairs on the central atom. Then moving on to our group 14 elements, specifically talking about carbon here, that's going to be the one you're working with the most. We have 4 valence electrons, so 1, 2, 3, 4. So you can see each one of the electrons is unbonded, which means most likely it's going to want to bond to another atom to complete the full octet of carbon. So with carbon, it's most likely going to have 4 bonds. And remember, when I draw it like this, it could look like the way I just drew it, or it could have 2 double bonds, or it could have a double bond and 2 single bonds, as long as it's adding up to 4 in total. Then we have our group 15 elements, which have 5 valence electrons. So if we were to do the dot structure for nitrogen, we have 1, 2, 3, 4, 5. So it's going to usually keep that lone pair and then form 3 bonds with those non-bonded electrons. So nitrogen is usually going to have a lone pair and 3 bonds. Then we have our group 16 elements. Those will have 6 valence electrons. And if we're doing oxygen as an example, we have 1, 2, 3, 4, 5, 6. So oxygen usually has 2 lone pairs and wants to form 2 bonds. So oxygen and again, that doesn't have to be 2 single bonds, that can be a double bond instead. Then we have our group 17 halogens. Those will have 7 valence electrons. So if we're doing fluorine as an example, we have 1, 2, 3, 4, 5, 6, 7. So you can see typically a halogen is going to have 3 lone pairs and 1 bond. So fluorine with 1 bond and 3 lone pairs. And then finally, we have our noble gases in group 18, which have 8 valence electrons, obviously except for helium, which only has 2 valence electrons because it's in the first energy level. So if we were to draw a noble gas like neon, for example, neon has all 8 of its valence electrons, so typically it's not going to form any bonds, but if it was, then it would be an expanded octet, and we will talk about it later. So now, using that information, I want to try some simple examples before we go into all of the rules. So first up, we have CH4. So we know from our last slide that carbon forms 4 bonds typically. And something that forms the most bonds is most likely going to be in the middle of the molecule. Something that only forms 1 bond, like hydrogen, is going to be what we call a terminal atom. So a terminal atom usually is something that only bonds 1 or 2 times, and it's going to be on the outside of the molecule. So since we know carbon forms the most bond, it has 4 valence electrons, which all want to bond out to become more stable. And here we have 4 hydrogens that each have 1 valence electron. And so what they will do is they will each share their electron to form a bond between the carbon and the hydrogen. So this would be the Lewis diagram for CH4 or methane. Then moving on to NH3. Now nitrogen, we remember from the last slide, has 5 valence electrons. So nitrogen, 1, 2, 3, 4, 5. So typically that lone pair stays where it's at, but those lone electrons, those single electrons, want to bond out to gain stability. And we have 3 hydrogens, each having 1 electron that wants to gain stability. So they will share and form a bond between each nitrogen and hydrogen. Then we go to carbon dioxide. We have 1 carbon. Again, when you see carbon, you can kind of just throw that in the middle because it typically is going to be your most bonding atom, so we can just assume that's in the middle. Then we have 2 oxygens. So I'm going to go ahead and split those up. And I know from drawing oxygen earlier, oxygen has 1, 2, 3, 4, 5, 6 valence electrons. So it's going to want to have 2 lone pairs, and it's going to want to bond out twice. So since these oxygens are terminal atoms for this molecule, both of the bonds are going to go to the carbon. And then don't forget to draw your lone pairs. Now, if you are doing Lewis diagrams like I am showing you right now, and you are not quite comfortable, I do recommend adding up all of your valence electrons and double checking that you have the correct amount. So for example, if we're going back to that CH4, we know carbon has 4 valence electrons. We know hydrogen each has 1, so 1 times 4 is 4. So totally, we should have 8 valence electrons. And we know we have 4 lines. Each line represents 2 electrons, so we do have a total of 8. Then moving on to NH3, we know nitrogen has 5, and each hydrogen has 1, and there are a total of 3. So this also has 8 valence electrons. So if you count it up, we have 2 from this lone pair, 2 from this bond, 2 from this bond, and 2 from this bond, which does equal 8 in total. And then looking at carbon dioxide, we know carbon has 4 valence electron, and each oxygen has 6 valence electrons, so it's a total of 12. So we should have 16 valence electrons. So I'm just going to go ahead and double check. We have 2, 4, 6, 8, 10, 12, 14, 16. So that's just a simple way to check that you have done your Lewis structure correctly. All right, then we have NH2OH. So you'll notice that the H's are separated. That's just telling you where the H's are going to be latched onto. So this is saying that these two hydrogens are going to be connected to this nitrogen, and this hydrogen is going to be connected to this oxygen. Now, how do we know what is the central atom? Now, if you are looking at an atom like this, where we know the hydrogens are terminal, how do we know which one is going to be the center, nitrogen or oxygen? Well, when they're not clear, like a carbon atom per se, you're going to look for the least electronegative atom that's going to go in the center. So if we're looking at nitrogen and oxygen, nitrogen is less electronegative, so we're going to start with nitrogen. I know I'm going to have my 2 terminal hydrogens on that nitrogen, so I have hydrogen and hydrogen, and I know hydrogen wants to form 1 bond, so that took up a total of 2 of the nitrogen valence electrons so far. And then I have an OH group, which means I know that O is going to have 1 bond connected to the hydrogen and 1 bond connected to the nitrogen. Now I need to remember my lone pairs. Nitrogen has 5 valence electrons, correct? It bonded out 1, 2, and 3. So there are 2 left. That's going to be the lone pair on the nitrogen. For oxygen, remember we have 6 valence electrons. It bonded out 1 and 2. So we have 4 left. So you need to put on oxygen's 2 lone pairs. And now it should add up to all of the valence electrons for NH2OH. But let's just check it just in case. We know nitrogen has 5. Each hydrogen has 1, so this would be 2. Plus oxygen has 6 valence electrons, plus that 1 hydrogen. We would have 5 plus 6 is 11, plus 3 would be 14. So we should have a total of 14 valence electrons. So 2, 4, 6, 8, 10, 12, 14. So this would be the correct molecule. All right, so here are the rules. If you didn't understand what I did on the last slide, I would definitely pause this and read through these rules and try to understand what I was doing. If you need more clarification on this, please let me know and I'm happy to do it for you. And then some little tidbits to remember to put in your notes if you are taking notes. Hydrogen will always have 1 bond. If you have a second period element, just know you cannot have an expanded octet because it does not have a D sublevel to expand into. Carbon will typically have 4 bonds. Nitrogen will typically have 3 bonds and 1 lone pair. Oxygen will typically have 2 bonds and 2 lone pairs. And your halogens will typically have 1 bond and 3 lone pairs. All right, so there are some exceptions to the octet rule that I want to go over quickly. The first one is an odd number of electrons with radicals. So a molecule like NO2 is going to have a single electron left over. That's because nitrogen has 5 valence electrons and oxygen each has 6, so that's 12. So we have a total of 17 valence electrons, which is an odd number. So we're going to have an extra electron that is unpaired. So if we were to try to draw this, my brain goes immediately to nitrogen being in the middle with my 2 terminal oxygens. I want to double bond these oxygens because that's where oxygen is the happiest. That's the easiest way for oxygen to bond. However, the nitrogen bonded out 4 of its electrons, there's 1 left. Now, we can't leave the structure like this because nitrogen is a period 2 element. Period 2 elements have 2 energy levels. Well, the second energy level does not have a D sublevel to expand into. So we cannot expand the octet. Right now, this has 8 electrons in the bonds and that 1 single electron. So it has 9 electrons in its outermost shell. So we can't do that. So instead, what we will do is we will take one of these bonds and we will bump it out as a lone pair to one of the terminal oxygens. So now if you're looking at this molecule, you can tell that nitrogen and the oxygen on the right are not bonding how they want to bond. So because of that, we need to calculate formal charge. So for the nitrogen in the middle, we have 5 valence electrons minus the 3 bonds minus the single electron gives us a formal charge of 1. So there is a positive charge on this nitrogen. Then for the oxygen on the right, we can see it's not bonding how it typically does, so we should probably calculate formal charge. Oxygen has 6 valence electrons minus the 1 bond connected to oxygen minus the 6 non-bonded electrons. So that gives us a -1. So this oxygen has a -1 formal charge. Now overall, the positive and a negative charge cancel out, which is why there is still no charge on the molecule as a whole. But this would be the correct Lewis structure for NO2. Another example of an exception to the octet rule is an incomplete octet. So boron, like we talked about on the last slide, has 3 valence electrons. So if it were to bond covalently, it's only going to bond out those 3 valence electrons and have no lone pairs on the central atom. So for example, if we have BH3, the molecule is going to look like this, which means there are only 6 total electrons being shared for boron. So that's an incomplete octet. And then same goes for beryllium. Beryllium only has 2 valence electrons. So if there was a molecule like BeCl2, each Cl would bond to the beryllium, but there would be no lone pairs on that beryllium. So total, there's only 4 electrons being shared for beryllium. And then we have an expanded octet. So an expanded octet, remember, can only happen if it's an element in the 3rd energy level or greater because it has a D sublevel to expand into. And it just is a way for a molecule to become stable that minimizes formal charge. So for example, if we have PCl5, we know phosphorus has 5 valence electrons, and since this has 5 terminal atoms, we know phosphorus bonded out every single one of its electrons. So 1, 2, 3, 4, 5, and they all went to a chlorine. And we know chlorine has 7 valence electrons. It bonded 1 out to phosphorus. So there are 3 lone pairs on each chlorine. So now you can see this phosphorus has a total of 10 electrons surrounding it because it bonded out all 5 of its valence electrons. Then we have XeF4. Now xenon is a noble gas, which I'm sure you are aware of. It is going to bond a little differently. So I'm going to put xenon right in the middle because I know fluorines are terminal atoms. So I put xenon in the middle. I'm going to go ahead and do my fluorines first because I know that's where they're going to go, and I know they only form that 1 bond and have those 3 lone pairs. So I'm going to start there. Now, xenon is a noble gas, which means it has 8 valence electrons. Look at the molecule I just drew. How many of the electrons are bonded out already? Well, we bonded out 1, 2, 3, 4. Now, those 8 valence electrons that xenon have don't just vanish into thin air. They're still there. So we have to draw them as lone pairs on that xenon. So since 4 are still left, we have 2 lone pairs on that xenon. So xenon has a total of 2, 4, 6, 8 in the bonds and 4 in lone pairs. So it has 12 total electrons. All right, let's do a couple more practices. So first we have XeF2. Again, I know fluorine are terminal atoms, so I'm going to go ahead and put xenon in the center. I know I have 2 fluorines, and I know fluorine wants 1 bond and 3 lone pairs. Now xenon has 8 valence electrons. I already bonded out 2 to the fluorines, which means I have 6 left. So I need to put those 6 electrons as lone pairs on the xenon. Now, if you are not comfortable with this structure, you can go ahead and add up all the valence electrons and make sure they are all there. And you could also calculate formal charge if you feel like that xenon is not satisfying the formal charge rule. So let's do that for XeF2. I'm not going to do that for all of them, just for time purposes. But xenon has 8 valence electrons. Each fluorine has 7, so that would be 14 total. So we should have 22 valence electrons. So let's go ahead and count those real quick. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. So they are all there. Now, since xenon looks a little funky to us, let's go ahead and calculate the formal charge of xenon. So we know xenon has 8 valence electrons, minus the 2 bonds, minus the 6 non-bonded electrons, gave us a formal charge of 0. And we know fluorine typically bonds how you see it, so we do not need to calculate formal charge. So this would be the Lewis diagram for XeF2. All right, now for NH4+. Now remember, this plus means we lost an electron, right? We have 1 extra proton than electrons. So just remember, if you are calculating your number of total valence electrons, we know nitrogen has 5 and each hydrogen has 1, so a total of 9. However, we lost an electron, so we should have a total of 8 valence electrons at the end. So we know nitrogen is going to be our central atom. We have 4 hydrogens that all want 1 bond. And now looking at this nitrogen, if I calculate formal charge, I know nitrogen has 5 valence electrons minus the 4 bonds would give us a positive 1 formal charge. So that positive is on the nitrogen. That is where it comes from. Then moving on to SF6, I can see clearly that S is going to be in the middle, and I have 6 fluorine atoms. I know each fluorine wants to form 1 bond, and it just so happens that sulfur has 6 valence electrons. So what it did here is sulfur bonded all 6 of electrons out to the 6 fluorines. Now remember, the reason it can do this is because it is not in the second period. So technically these extra electrons are going to be filling into the D sublevel that is open in that energy level. So the fluorines are bonding how they want. If you wanted to calculate the formal charge of sulfur, you could. It's 6 valence electrons minus 6 bonds gives you a 0 formal charge. So this would be your Lewis structure, and if you wanted to count the valence electrons, you could. Then we have BF3. We want boron in the middle. We have 3 fluorines. Remember, boron only has 3 valence electrons, so there's no lone pairs on that boron. It bonded the 3 out, they're gone. And then don't forget to draw your lone pairs on fluorine. All right, so coordinate covalent bonds. So a coordinate covalent bond or a dative bond is a type of covalent bond where both electrons in the shared pair are donated by one of the atoms involved. So if we look at the 2 molecules, NH3 and BH3, we know that the nitrogen in NH3 has a lone pair on it. We also know that the boron in BH3 does not have a lone pair on it because it only has 3 valence electrons. So if these two molecules were to join and become one molecule, what would happen is that the lone pair on nitrogen would be donated as a bond between nitrogen and boron. So our final structure would look something like this. We have our N to B bond, and we have our 3 hydrogens on each atom. And that central bond there, that would be the coordinate covalent bond or the dative bond because both of the electrons came from nitrogen. Now, how do I tell if a molecule is polar or not? I know first you can look at the bonds and see whether the bond is polar based off its difference in electronegativity. But in reality, what we're really looking at is whether there is a dipole in that molecule. If the dipoles do not cancel out, it will be a polar molecule. So looking at this SF4 example on the bottom left here, we can see that the fluorines are very electronegative, so they're going to be pulling electrons away from that sulfur. But just remember, this lone pair on sulfur also pulls electrons. So that's going to be an unequal sharing of electrons, and our dipole is going to go away from that lone pair. So that would be a polar molecule. Same with nitrogen with its 3 hydrogens. There is a lone pair on that nitrogen, so there's automatically an unequal sharing of electrons, which means there will be an overall dipole. So that would be a polar molecule. Now let's focus on what would classify a nonpolar molecule. So a nonpolar molecule can exist in 2 ways. Number 1, if it's made up of all nonpolar bonds. So at this point, you should know that a carbon to hydrogen bond is nonpolar. So if you have a molecule that's made up of all carbons and hydrogens, you know that automatically it's going to be nonpolar because there's no polar bonds in that molecule at all. So hexane over here, hexane is nonpolar because all of those bonds in that molecule are nonpolar. So it can't be polar. Then the other way a nonpolar molecule can exist is if it has dipoles, it has polar bonds, but those dipoles cancel each other out. So for example, if we have CCl4 or carbon tetrachloride over here on the right, you can see that that carbon has 4 chlorine atoms all pulling at the exact same rate. So those dipoles from chlorine, they're going to cancel each other out, and overall there's no net dipole on the molecule. So that would be a nonpolar molecule. And then let's close out this video with this quick question. It says, consider the molecules CF4 and SF4. Draw the complete Lewis dot structure for each molecule. In terms of molecular geometry, account for the fact that CF4 is nonpolar, whereas SF4 is polar. So let's start with CF4. We know carbon is going to be in the center. We know we have 4 fluorine atoms. We know fluorine wants to have 1 bond and 3 lone pairs. And then you could go ahead and check your number of total valence electrons if you wanted to be sure. And then let's go ahead and do SF4. So sulfur is going to be centralized. We have 4 fluorines again. We know fluorine wants to form 1 bond and have 3 lone pairs. However, unlike carbon, sulfur does not have 4 valence electrons. It has 6. And it only bonded out 4, which means there are 2 left. Those 2 don't just vanish, they are still there. So there's actually a lone pair on that sulfur, which is why SF4 is polar and CF4 is not. Because in CF4, all of those dipoles are canceling out. Well, in SF4, there is a lone pair that also pulls at a different rate than the fluorines, which is an unequal sharing of electrons. So that is why SF4 is polar and CF4 is not, because sulfur has a lone pair on its central atom. All right, I hope that video helped. If you have any questions, please let me know. I'm happy to help. Have a great day.